I want to talk to you about the atomic structure and radioactive decay. We have learned about the three subatomic particles, protons, neutrons, and electrons. And remember, we said that the protons were positive, neutrons were neutral, and electrons are negative. And they are located in different parts of the atom. So the electron cloud, the big brown circle, is mostly empty space and contains only these negatively charged electrons. Inside the nucleus, we have the protons and the neutrons, and the nucleus is very small and very dense, and it is the location of all the mass of the atom. Now, what keeps the electron cloud attracted to this nucleus is this electromagnetic force. Because the nucleus only has positively charged protons and neutral neutrons inside it, its overall charge is positive. And because the electron cloud only has the negatively charged electrons in it, the electron cloud has an overall negative charge. So this positive and this negative will attract, because we know that opposite charges will attract. So even though this nucleus is really small and the electron cloud is really big, the electron cloud is attracted to, pulled toward that positively charged center. Now, these protons that are inside this nucleus are all like charges, and we know that like charges repel. So what keeps them inside a very small nucleus is the strong force. This strong force keeps the protons inside the nucleus against their will. It's what's responsible for keeping the nucleus stable. If you consider thinking of like a prison, the guards keep the prisoners inside. The prisoners don't like each other and they don't want to be there, but because you have guards on the perimeter of that prison, all of the prisoners stay inside against their will. Now, every now and then, one escapes. And I've got this little orange wave here to represent something escaping. When they escape, this is called the weak force. And it's when the ratio between protons and neutrons gets too big. In other words, I have a lot more neutrons than I do protons, and that nucleus will get too full. And eventually, a neutron will find a crack in the wall and will escape the nucleus. Or maybe some protons and neutrons will leave together. And when that happens, what we will say is that the nucleus is now unstable. And that is what causes radiation. Now, gravity is also a force that we need to list here. All of these are forces, but gravity at the subatomic and atomic level has very little effect on what we see happening inside an atom, so we don't really worry about it. Okay, so there are three different particles and rays, or three different forms of radiation that we can talk about leaving an unstable nucleus. And we have alpha, beta, and gamma. Now, alpha particles are a helium nucleus. So it's a nucleus that has two protons and two neutrons. Well, protons are positive and neutrons are neutral. So this alpha particle is positively charged. A beta particle is actually a neutron that has hit itself against the barrier of the nucleus and split into two parts. It splits into a proton and an electron. Now, when it splits, it's still inside the nucleus. And a proton looks like other things that are in the nucleus, so it stays behind. It's a proton. And so the nucleus has gained a proton. But this part of the neutron that is the negative part, this electron, does not belong in the nucleus. So it escapes to the outside of the nucleus. But it doesn't stay in the electron cloud, it keeps going. And this is the beta particle that will escape. So we write it as an electron, the E for the symbol of electron, 0, -1. And we'll talk about what the numbers mean more later. So the overall charge for a beta particle is negative. Now, a gamma ray does not have a charge. And the reason is because it is pure energy. It's not any particles. There's no protons or neutrons that are escaping with gamma radiation. Now, what is usually true is the gamma radiation will be sistered with or paired with alpha or beta decay. So if you have one, you usually have the other. Now, I have these three different things written here: paper, foil, and lead. That's because when we're talking about radiation, we want to talk about how we can protect ourselves. Well, alpha decay can be stopped by a sheet of paper. It cannot penetrate our skin. In fact, the only way alpha radiation could hurt us is if we were to swallow it. Now, beta decay can be stopped with a couple of centimeters or millimeters of foil. So like your sheet of aluminum foil could protect you from beta decay. Gamma radiation requires several centimeters of lead before it can be stopped. So paper, foil, lead, that means that gamma radiation has the greatest penetrating power and alpha decay has the weakest. Now, the benefit for alpha decay is that you lose the most particles out of it. When a nucleus has this unstable nucleus, this unstable condition, its objective, the reason it wants things to leave the nucleus, is so that it can become stable again. So alpha particles are beneficial to the nucleus because it allows 2 protons and 2 neutrons to escape. That's 4 less things that are left behind in the nucleus. Now, a beta particle is not as useful because you basically only lose half of a neutron, this electron that escapes from that nucleus. And gamma radiation has no particles that leave with it. Now, some applications for these things: we use alpha decay in our smoke detectors in our home. And if you've ever gone for a CT scan or other radiology tests that require you to drink some bad tasting stuff, or they put you up with an IV that puts some things in your circulatory system, they will have a tracer in there. They'll have this isotope that decays quickly and safely in your body, and it gives off beta radiation that the X-ray machine can pick up. Now, gamma radiation is what we use for radiation therapy when we're treating cancer. You've heard of chemotherapy and radiation therapy. Now, radiation therapy is when we harness these gamma decay waves and target the area that has a tumor. Okay? When a nucleus becomes unstable, its primary objective is to become a more stable substance. And the only way it can do that is to decay, either through alpha, beta, or gamma decay. Now, as it decays, it's going to change from what it started out being into something else. And so we have this term half-life. And what a half-life is the amount of time that it takes for half of a sample to decay. Now, the shorter the half-life, the more unstable the substance is. So if I have a substance whose half-life is 3 seconds, I know that that is a very volatile substance. It's very radioactive and unstable. But if I have something whose half-life is 14,000 years, then I know that that's a very stable substance, and it takes a long time for it to decay. Now, the best way to solve half-life problems is to memorize this chart. And what it does is it organizes for us everything we might possibly need to solve for. So we have half-life, time, amount, and fraction. Now notice that half-life and time both start at 0. Your time always starts at 0. And before time begins, I have all of my sample, so my fraction is 1. But on my very first half-life, by definition, the half-life is the amount of time it takes to lose half my sample. So 1 half-life, I have lost half of my sample. 2 half-lives, I only have 1/4 of my sample, and so on and so on. Now notice that my time column and my amount column are blank, because for each problem, these answers here will be different. But what will happen is whatever amount I start with, I will write here, and then as I go down, I will divide by 2. And whatever I am told the half-life is, whether it's 4 seconds or 4,000 years, I will write the value for 1 half-life here, and then add it to itself every time I go down. So let's look at an example of a half-life problem. How much remains of a 100-gram sample with a half-life of 20 years after 3 half-lives pass? So you notice everything that's in brown is the same as the chart that we had before. Now I identify my knowns, 100 grams in 20 years, and I put the 100 grams in under amount. That's how much I have when I start. So at time 0, all of my sample is 100 grams. Now, my half-life is 20 years. That means that for every half-life that passes, it's going to take 20 years. So my first half-life is 20, my second half-life is 40. Now notice that my third half-life is not 80. It's not this times 2. It's this plus itself again. So every time I go down, I add the half-life to the total. Now, I want to find out how much remains after 3 half-lives. So what I need to do is take my original amount and divide by 2 until I get to my third half-life. 100 divided by 2 is 50, divided by 2 is 25, and divided by 2 is 12.5. So I know that I only have 12.5 grams left of this 100-gram sample that has a half-life of 20 years. Now, some other nuclear reactions that occur are fission and fusion. Fission is what we use in our nuclear power plants, and fission means splitting of the atom. So a good mnemonic or a memory device for me to remember is fission is division. Fission and division sound very similar. So splitting would be a dividing of an atom. Now, fission is not natural. It does not occur naturally. We have to make it happen. It produces a lot of radioactive waste, and it requires critical mass, and it requires a stream of neutrons to be fired at this substance that will make it unstable. Now, fission is very useful because it produces 1,000,000 times more energy than our other normal chemical reactions. So that's the reason we want the nuclear power, is because it produces a lot of energy for us. Now, it's not as useful as fusion. Fusion is when we're combining the atoms together. So we take 2 nuclei and fuse them together. They occur naturally in stars, and there is no waste. Now, the problem is that you have to have a very high density and very high temperature environment. Think about a star and how hot a star is, like our sun. So that's not very practical here on Earth. It produces 4 times more energy than fission. So this was 1,000,000 times more energetic than any other reaction, and this is 4 times more energetic than fission. In several problems that you will see, you will be asked to identify what type of reaction is occurring based on what you see written, and you're also going to be required to solve some alpha and beta equations. So I want to compare the four of them for you now. An alpha equation, the way I know that I have an alpha equation is when I see this helium nucleus, atomic mass of 4, atomic number of 2. Now, this looks more complicated than it is. If you ignore for a moment the symbols and just look at the numbers, this is a simple addition equation. 218 plus 4 is 222. 86 plus 2 is 88. Now, where the different numbers come from are from the periodic table. This bottom number is my atomic number. So what this equation is telling me is I've started with 88 protons. I look on my periodic table, and atomic number 88 is radium. So I'm going to write Ra. Well, when I have alpha decay, 2 of those protons leave. That leaves me with 86 protons left. I look on my periodic table, and I find out that 86 is the atomic number for radon. So I have to change my symbol when my proton number changes. The atomic number of 2 is helium. So the symbols are simply changing to match the bottom number from the periodic table. And the top number is just subtraction. 222 minus 4, I'm left with 218. Now, beta decay is a little different. I'm going to have this loss of an electron, a gain of a proton. Since the protons are listed in the bottom, I'm going to show those as a -1. Now, the reason I do a -1 is because I need this side to be higher than what I started with in beta decay. I'm gaining a proton. So if I started with 6, I need 7. So my particle symbol has a -1. That way 7 plus -1 will equal 6. Now notice the top value doesn't change. That's because the proton came from that neutron splitting up. So when I had this neutron over here in the 14, it split up. I lost a neutron, so it went to 13. But I gained a proton, so it went right back to 14. So this number never changes, and I have this top value of 0 to show that. Now, in fusion and fission, you might see helium, but the difference is that what's on the other side will either be 2 small objects being combined to 1 larger object, or it will be 1 large object being split into 2 smaller objects. Now notice that smaller is relative. This is not a small atom. It's got 56 protons in it. But in relation to what it started at, 92 protons, it is smaller than what it started at.